Warm greeting, my dear students, and I am Dr. M. Prithviraj, Department of Mechanical Engineering, Assistant Professor, and we are here about to see the thermal engineering, especially on velocity triangle. And this is one of the topic students find it most difficult to understand actually. So that's the reason why I actually brought up this topic to the video. And I'll explain the video. Before getting into the video, let us discuss what are the types of turbine basically available, and reaction turbine and impulse turbine. From the picture itself, we can clearly understand what is meant by reaction turbine and impulse turbine. This is the reaction turbine. When the water is coming out at a force, it tend to rotate. With the help of the water exiting force, the turbine rotates. So that's how the reaction turbine works. That is why it is called reaction turbine. It is reacting to the force of water outwards. And impulse turbine, impacting of nozzle, impacting of water created by the nozzle on the turbine. So that's the reason why it is called impulse turbine. This impulse turbine is rotated by the impact force of a nozzle, and this nozzle used to create a water jet which impacts the turbine so that it tend to rotate. So that's the reason why it is called as impulse turbine. So these were the both basic types of turbine which is available practically. And for both turbines we have a velocity triangle. So this is how the turbines is formulated. This is how we have to calculate the parameters of the turbines. And consider this is a blade, consider this is a bucket, and this is blade velocity, and the water coming in inlet from the nozzle. So water coming in velocity which is called as V1, velocity at inlet. The water striking the blade and getting out, which is actually called as V2. So that is inlet of turbine is V1 and outlet of turbine blade is V2, and the reaction turbine is actually called as VR1. VR1. Here it is VR1, and the outlet reaction turbine is outlet of reaction velocity of a turbine is VR2. I will draw once again so that you will get a clear cut idea of what it is actually the velocity triangle. And this is the blade or the bucket, and from the nozzle the water will impact in the turbine, which is actually kept almost of 20° to generate more impact to the turbine. So that's the reason why nozzle is kept at 20°. If it is in 180°, the impact will be less. If it is in 90°, it won't even impact. So that is the reason why nozzle is kept at 20° of inclination. And this is V1. It is hitting the turbine and leaving the turbine at V2. So the inlet velocity is V1 and outlet velocity is V2. And the reaction force of a turbine, the reaction force of a turbine VR1, the reaction force of a turbine at the exit is VR2. So here it is, the reaction turbine, which is a collective cumulative force of a inlet velocity, and the outlet velocity of collective cumulative velocity, it is referred as VR2, and that longitudinal tangential force which will be denoted as VW, tangential force which will be calculated as VF1, and here it is VF2. Since it is in V inlet section VF1, since it is in V outlet section VF2. So this is how the velocity triangle used to have, and we will have a clear cut idea so that how the velocity triangle can be framed. I will show it to you so that you will get to understand what is meant by velocity triangle. Even in fluid thermodynamics we have, even fluid dynamics, and in thermal engineering we have this velocity triangle. Students find it most difficult to understand. So that's the reason why I came up with this, and I will draw the velocity triangle once again so that the cumulative velocity triangle, so that you can formulate. So this is a nozzle, and this is the water impact V1 and water leaving after impact V2, and this is VR1, this is VR2, and the longitudinal force, tangential force VF1, this is a tangential force VF2. This inlet section and outlet section was drawn simultaneously so that you will get a cumulative output. So that VB is actually denoted as blade velocity, and we will start with the blade velocity to draw. VB will denote it as A and B. This is point A and this is point B. So this is called as velocity of blade, and from A you will have to draw V1. so that you will get an angle of 20 degree. As I mentioned earlier, nozzle is kept at 20 degrees, so receive the maximum impact. So V1 at 20 degree of nozzle angle, this is the line, and the reaction force from the beta point will have to be drawn like this, so that VR1. So V1 and VR1 was drawn, and this tangential force we have to draw as a straight line. So VF1, this is wholly of the inlet side, VF1, V1, VR1, and this is how the inlet triangle looks like here. So this is what the inlet triangle looks like. I will draw drawn as the inverted triangle, so that you will get to know what it is. So and we will change the color. So that VR1 is at entry level, and VR2 is at exit. So VR1 is at inlet, VR2 respective to VR1 is at exit. So that if we assume that inlet velocity and outlet velocity have similar ratio of speed, so that we will come to a conclusion of VR1 is at similar speed or similar velocity of VR2. You can draw a line, similar line, and VR1 inlet, VR2 outlet, so that you will come to know V1 is inlet and V2 will be considered as outlet, and the tangential force is Vf2. So that you will have to conclude the diagram, and this is how the velocity diagram looks like. And in YouTube or even the books, you will get to know diagram only, they will draw it as inverted triangle. You can also draw like this, but you will never find of inverted triangle of this. So this is easy to understand, so that's the reason why I have brought out this inverted triangle of what you actually seen in book or in video. So this is how you have to draw, and from B to this point we will consider this as F, we will consider this point as E, we will consider this point as E2, since it is an outlet, F2, F1. So from point F1 to B, that is VW1 whirl velocity, and W1, and this is VW2. So cumulatively VW equal to VW1 plus VW2. So whirl velocity is nothing but if a nozzle is impacted, tend to impact, it won't have a narrow stream, it will have similar kind of whirling within the stream. So that is what considers velocity of whirl velocity. So the maximum whirl velocity will be obtained only after it impacted the turbine. While coming inlet, at the inlet it will have a narrow stream, so that the inlet velocity of whirl will be lesser when compared with the inlet whirl velocity of exit will be have much more of whirl velocity. So that's the reason why inlet whirl velocity have similar area, whereas outlet whirl velocity have a larger area. So this is how velocity triangle should be drawn, and we will see similar kind of problem for the same velocity triangle in next video. Thank you.